Welcome, everyone. My name is Annie Burgess. I am the ESIP Lab Director, and I'm the room host and co-chair for this session. Just a few announcements before we get started. A reminder to everyone that ESIP has a code of conduct that you can find in the notes section for this session. Reminder to mute when you're not talking, but we would like to see anyone's face who feels comfortable having their camera on if we're discussing things or asking questions. Also, a reminder to use the chat to say hi and let us know where your name and where your affiliation and where you're from, or kind of where you're located in the U.S. And with that, I'm going to turn it over to Jensen.
Thank you, Anne. So this session, we will have 4 speakers. Me and Liang Zhao, Professor Liang Zhao from George Mason, and he is also this year's NSF Career Awardee. He is going to Emory University this 4th semester. And also we have Nana, right? Are you there? I think we need to, yeah, probably. And we also have Diego from Columbia University. So we have 4 speakers, and each one will focusing on a different topic. Everyone will have 20 minutes presentation. Then we will go to the Q&A session. So I'm gonna share my screen and start. Okay, let me start the timer for me. Okay, so everyone see my screen okay?
Yes.
Okay, great. So hi everyone, I'm Ziheng Sun from George Mason University, and this is a project that is firstly funded by the ESIP lab, and it's called the GeoWeaver, and then it's later funded by the NSF Geoinformatics program, and we are working on this project for more than 2 years, I think, almost 2 years. So what we are working on is trying to affiliating the adoption of AI technology in the earth science. So before I introduce the workflow, let me look at the state of art of AI in the earth science. Before we introduce the AI in earth, we first introduced AI models. Right now, I think there is typically 2 kinds of AI models in the market. The first one is non-neural network. So it means it doesn't use neural network technology. It has a lot of algorithms, like a regression, the decision tree, random forest, SVM, naive Bayes or AKNN k-means. All these classic algorithms, they works perfect in many cases, and it has been adopted in many, I think, industrial or either the academic projects for many years. So people trusted all these models. They work smoothly at most time, but they also have some drawbacks, disadvantages. So people are looking for more intelligent and automatic solutions. And from the computer science, they introduced the neural network. That is actually a very ancient technology, but it has go down and go up several times. And recently it has been popular again. So we already seen a lot of successful stories from in the computer science domain, like computer vision domain especially. or the natural language processing area. And all these models are introduced to earth science. Like the most Euro models we have seen is multi-layer perception, which probably have been used in earth science since maybe 20 or 30 years ago. But the recent development on the CNN and ION, which is convolutional neural network and recurrent neural network, the rising of these neural networks, most of them are deep neural network, which means they have multiple hidden layers, and those neural networks will be very complicated, and it's a black box, and training them and making them to learn the patterns, and after all, the model will not be understandable to human beings, and people are trying to understand it, but that is still ongoing work. So based on the neural network, we have derived all those networks like a ResNet, residual network, LeRNet, VGG16, LeRNet, oh, this is double, that must be duplicated. So DeepLab V3, the mask RCNs, all these are different kind of neural networks. It's a derived categories. And most of them can work perfect because they are all backed by some research results that has been proved usable, or it has the results that outperforming the existing approach. But nobody know whether they will do the same or they will have the same results in earth science. That's still in question. So I have looked into the history, the research history, all those public literatures about how people are using AI technologies in the earth science. The first one is a solid earth. People having started using the AI technology, starting multiple earth science problems, like the earthquake prediction, probably. And this one has been started since at least since 2003, and this Zamazek, right? They're using the decision tree to predicting that earthquake. And the other people like Connor are using the multi-layer perception, and this Hausman are using the hidden marker model, and they are using the random forest. One is using LSTM. So you can see that before 2017, most people are still using the long neural network. And this one is actually, it's a very basic one. So it's not the latest neural network model. So after 2017, the major model used is mostly random forest and LSTM. So it means that in the long neural network category, random forest is very popular in earthquake study, and the LSTM is the neural network-based approach that is popular for earthquake study. And the Volcano is the same thing. Their own has started using the Green's function, which probably is another machine learning method, and the TDOS is using deep neural network. The Mayer used the kernel-rich figurational model. And Landside, the same thing. Most of people are reusing the technologies. They are not inventing the new technologies here, like the regression, the AN, the artificial neural network, SVM, and deep convolutional neural network. And the most, most active areas are used that is adopting the AI technology is net cover and net use. So too many papers are talking about how to use AI model to recognize object from the remote sensing image from the field collected observations. So all those so in this area, probably this area is the most active domain that is exercising the AI technology in this solid earth science. And in hydrology, in the rainfall area, you will see that a lot of SVM has been used. And besides, many people, in 2004, the multi-layer perception has been used to predicting the rainfall. And most other researchers are studying the SVM, and this Xinjian used the convolutional LSTM in 2015. And for the surface water, most researchers are still using SVM. So SVM and LSTM and ANN are the most popular method in the surface water research. For the groundwater, the SVR, multi-layer perception, and the regression tree, and the same methodology here, SVM and regression. This is the decision tree. So you will see that Nakano found that in last year, the random forest is better than regression and decision tree, which I think you will replicate this result in many other areas. Random forest is actually better than many other decision tree and the regression methodology. And snow and ice, people are using wavelet ANN and regression, ResNet, ANN, and CNN. In the atmosphere science and the climate change, I haven't found many papers on people are using how they use the AI technology to study climate change, because people are still using the physics-based model to do this, and the result is it's unclear whether the AI will perform better, or what's the position the AI should play in modeling the climate change. So that's some areas that need people still to look into. And for the hurricane and drought and wildfire, air quality, there are many scientists are using AI technology to study the, the AI technology is basically a black box, but atmosphere scientist is a traditional physics-based modeling work. So it's really surprising that we have seen so many people are already exploring this option to merge, I think, to integrate the AI technology into their existing numerical model. And among these studies, I think I needed to emphasize that hurricane research, it seems, is the most active area in the atmosphere science on the adopting AI into their modeling work. I think you will see that after 2017, there are many papers talking about how to use a convolutional or recurrent neural network on studying the hurricane. So after I read all those papers, and I found that many people are asking the same question. So why AR is actually not working very well in earth science than it works in the computer vision or computer science domain? So I think this should be some kind of very fundamental question for the Earth AI. If you want to implement Earth AI, we should ask this fundamental question: why it doesn't work as the same, at least the same as the computer science? So I think, so in my opinion, that the most important problem is the generalization problem, because if you look at the problem, the scientific problem in the computer vision, you will see that the one simple problem probably requires massive data to cover like more than 19% of the possibilities. Let's take this one as an example. So this is the autonomous driving, and if you want to regularize the street view, you will have this class hierarchy, right? But the scene is basically it's very consistent. It only has a field. It only has a road, the trees, and the roadside, probably curbs, and the residential houses, something like that. So it's so the image, the data is very consistent. It's continuous, and the possibilities is not that many, right? But when the situation turns to this one, the possibilities will exponentially increase. And if you want to get a data set to cover like more than 19% of the possibilities, probably you will need massive data to train your models. And that's why it's really hard to generalize your model, which can be used, other than their training area. So all the AI models which are trained, it's basically can only be used in the same area. It's not probably it's not easy to transfer your model to other areas or in other study temporal period. So I think the major reason of failing of AI in earth science is because the training data set. The training data set takes like 70% of the reason, and algorithm is only 30%. So in overall, the adoption of the neural network-based AI technology is still in its infancy stage, and many of scientists still trust the well-established machine learning, like regression, the random forest, and neural network because of its higher cost. So it's still not very widely used, at least not in the industry application. So next I'm gonna introduce to accelerate the adoption of AI or the experimenting how to integrate AI and to help us science to improve its research process or increase the information extraction process from the Earth data. We want to create some workflows. Workflows will help us to automate the process. So the adoption of AI technologies like neural network technologies were not that hard for us to try. And the entire AI workflow, it has several steps like this one. So first, it has downloading data from multiple source providers, and then pre-processing the data into AI-ready format, and then feeding the data into models, and the training and testing, probably the validation. We have to loop in the process until we have a satisfying model. And then we need to deploy the model for data production. But all this work is very long, time-consuming process. So how can a scientist to do this easily? Because we are not, computer scientists. We are not very familiar with this computer science, concept, technologies, tools. How can we do this more easily? And it will help us to accelerate the research process. So I have created several equations to explain how to explain their cost, like the workload on the person and machine. So on the person and scientist, if you look at the equation, you will see that the time spent on the pre-processing and the train test and the validation processing and the AI algorithms, the complexity, the hyper parameters number, and the distribution pattern of the training data set. These parameters are all matters on the impacting the workload of the AI work. And this parameter is the automatic level of the workflow. If we increase this parameter, we will have the workload on the person will it will be significantly reduced. So everybody will be, it will become easier for people to experiment AI on their own data set. So how to enable the computing for Earth AI? Because the Earth data is very big, and the training on the Earth data will take a lot of computational resources. So how to accelerate the training? So first, we need to look at the platform we have. So we have the supercomputers. Supercomputer can do this work actually, but most of them are equipped for running the MPI processes, I believe. Most of them is not being used for like using the CUDA or GPU processing. And the cloud computing, it has a GPU, it has the AI training platform, but it's a little bit expensive. So high performance computing servers, PCs, laptops, and the smartphones, and recently they have developed a smartphone-based processing framework, I think. So the GPU is mostly essential for the training on the Earth data, and we need the algorithm improvements to reduce the complexity. And this is a major barriers for the Earth AI. So I'm not going to go through this in details because of time. So what we're trying to have, what we're trying to achieve is we want to, the scientists, because it's difficult for scientists because there are multiple platforms right now for training purposes or for the pre-processing or post-processing purposes. And the Earth scientists have to jump from one platform to another. And maybe in the process, because everyone is very busy, right? Once you've got your processing is still working on some kind of cloud, and the cloud is expired or the resource, though the VM is crashed, you will lose everything. All this code, data, the results will be gone. And we are trying to manage all those platforms. It will be quite a challenge for all these scientists or Earth scientists. So we are proposing a tool in the middle of the resources and the Earth scientists. So it will help you to manage all the code, all the resources. It will separate the code from the resources. When you want to run some AI workflow, you will assign each process onto specific platforms, so it can be run in the specific platform, but the code is still under control. You will not lose your code once the platform is crashed. So everything will be stored here, not here. But the code will be transferred to here because this is where the data is, right? All the data is in here. The code will go with data, not the data will go with code. So that's the major purpose of this tool. And existing solutions, so we have workflow management software, but I think they are a little bit higher at the entry barriers. So most of them have many users, but you have to learn about the how to use them, and you have to adapt yourself to them for a while. So our solution is GeoWeaver, and the GeoWeaver is promising to be a user-friendly and low entry level, low barrier of entry workflow management system. So it will have three concepts. The first one is host. Host is a platform like a VM or a private Linux server, a laptop, anything like a infrastructure. A computer will be as a host. And the process is all the shell scripts, the Python and the Jupyter notebooks will be a process. Workflow will be linking multiple processes into one flow graph. So it will present experiment. So this is how the GeoWeaver looks like. The right panel will list all the resources, host, the process, and the workflows. If you click on one of them, you will see all the code on the left window. If you click run here, you will have the option to select which platform you want to run this process. And you will be able to check all the provenance information by clicking on the history button. And if you click on the details, you will see both the code that was executed and the output log. So you will have all the information. You can trace the change history back. So you will know that why the workflow works then, but it doesn't work now. So you have fully control of the process. And besides, you will also have access to the result server, result files, by using the file browser button on the host, on the hoster resources. So it has several features. Like the first one is integrating the public and the private resources, and it can record every run of the AI workflow. And it will help you to synchronize your code and make your scripts, all the related code under control. And it will automate your AI production workflows by linking all those different platforms. And this is a vision of if we manage all these workflows using tools like GeoWeaver, and we will have the efficient AI engineerings and the traceable, explainable Earth AI models. And it will make the workload pretty affordable by every scientist. And it will make the knowledge and pipelines of AI shareable and reproducible. Yeah, so in conclusion, an AI GeoWeaver is one solution we proposed as a user-friendly, one-stop, and cloud-oriented workflow management system for Earth AI workflows. And this is our funding information. And thank you.
Thanks, Jensen. Let's see. Who are we passing it over to now? Well, first,
if you are finding me, I'm the next. Okay.
Okay, you should be able to share your screen. Jensen, do you want to hold questions until the end and just go through our?
Yeah, let's hold to the end.
Okay. Do you want to try screen sharing?
Sure.
Now, Liang? Okay.
Okay, so are you able to see my screen?
Yeah, we see your full desktop now.
Okay, great. So I'm just
or we see PowerPoint, everything.
PowerPoint start.
Now we, oh, there you go.
Yeah.
Social media mining. There you go.
Yeah. Hi, everyone. So today I'm going to introduce the topic, so-called social media mining for spatial temporal event forecasting. As you can see, the combination between two parts. One is the social media mining, and it's technical and applications related to the spatial temporal event forecasting. So I'm a person who actually sit in the domain of data mining and machine learning, but I'm interested in the spatial and temporal as well as network data. So I just want to talk something from my perspective. So because this is actually a big domain, I cannot exhaustively cover all of the technical details. So I selected to introduce the background research challenges, and one of the representative method in that, although we have hundreds. And then in the end, I will give you the tutorials and the survey papers for those people who are interested in knowing the details. So first of all, I want to introduce what are the so-called social events or societal events. So I'm giving several examples in the following slides. So the first one I want to introduce, I guess all of us are familiar, is the epidemics outbreaks, or the pandemic outbreaks currently happening. So in this example, we use the CDC data to visualize. As you can see that the warmer the color, the higher the activity level is. And it in the first week, the activity was very high in the southern area in the US, and you can see that gradually it can just diffuse in the spatial temporal space. The other example is the terrorism events in Africa. As you can also see that the different dots in the region denotes the different locations, and they also come with time and their specific topics and the reasons of the events. And the next one is the traffic congestions. This specific example is actually big events in Atlanta 4 years ago when one bridge was broken by the fire and the heat, and then it further caused the mass. So it's very big traffic congestion on the contiguous road segments, and also further caused the other traffic congestions, because a lot of traffic flow took a detour to other locations, which finally resulted in some very big congestion over the whole city. The other example is the civil unrest events, so including, for example, protests, strikes, and as well as many other riots related events. And each of them, they typically have location and the specific topics, because people doing the project, doing the protest for some purpose. We also have the economic crisis, which is typically happen in temporal domain. We also have the events like the earthquake events. So I just want to kind of raise up several the above examples, but as you can see, there could be a lot of other events that could significantly influence our society and the nature. So here are kind of a little bit more examples by this word cloud, but as you can expect, there could be there are actually much more types of the events that we want to care about. So now I want to discuss about the possibility about whether they are forecastable, whether we can forecast those events, and because of the high benefit behind it, right? So the first example I want to raise up is the so-called civil unrest events, because it seems to us that civil unrest is one of the most kind of significant and complex type of event among all of different type of events. So for a civil unrest event, typically people have reason to do this, because it takes a lot of efforts and risk for them to do that. So they have strong reason. The strong reason typically comes from the complaining, and then and this complaining is not unobservable. We can observe it because people will need to complain in the public domain, especially in social media, and we can observe the semantics and also spatial patterns. And once people get an agreement and their complaint still cannot be, the issue still cannot be solved, people will further step out to plan the potential events. And they could plan the time, location, and topic, and whatever the slogan, whatever on the public platforms such as social medias. After that, they will try to advertise their planned events. And because everyone cannot know everyone's phone number, so they will still need to use the public channels such as social media to disclose it. So as you can see, all of this stuff are actually observable, and all of them are happening before the event occurs. So how about we can track them So then if we can, dig out these patterns, and so then we can anticipate the future potential events for the sequence rest. And the other one is the example in traffic domain, transportation congestion, as the one I have raised up in the beginning. So still the same one. So as you can see, the first event was happening on the bridge because that was broken by a fire. And actually, if the system is smart enough, we expect that it could anticipate that, okay, there are going to be some congestion because this road has been broken, right? So the upstream one should be should be blocked, and we can further step out to further anticipate that, okay, there could be some traffic flow that they're gonna detour to some other road, and we may predict what other road are, right, based on our historical traffic patterns. So we can predict other event number. We can predict other congestions, congestion number 1, congestion number 2 in different locations before it actually happening. So this is going to be very important for us for the traffic management. The third one I want to just raise up is epidemics domain. So epidemics is also forecastable based on the for example social media data. This is because epidemics happens because of the underlying mechanism. One is due to the contact network, the disease contact network among people. And beyond that, we also know the health status, the disease status of individual people. We have the models of them. But the only thing that we don't know is the current status of every single people. So if we know that, if we know whether they are in which health status, and we also know that how they are connected and how they will connect it, and whether they have be isolated or not, and whether they have taken flu shot, we will be able to anticipate their future trends. And seemingly, a lot of these patterns actually can be observed from the social media. For example, we can observe whether some people took flu, and we can also know that whether people has been isolated or not. And also we can also even track the health status of people by tracking the social media postings of the people by multiple days. And so then we can possibly even observe the flu duration, right? So which is a very important parameter. So we can then input this important parameters into the underlying mechanism model. I will not talk about that in too much details. The expectation is that, okay, we have hope to do the social event forecasting in several domains. And so next question is that how we want to do that. So because I'm a data scientist, I of course will think about a generic way, as long as I have a large amount of historical data. So can I learn the end-to-end model that can do this job? So from machine learning point of view, it is very natural to formulate this problem as a supervised learning problem, where we have the so-called social encoder, so-called social indicators, which can be typically social media or other sensors we have. And we then develop a model that can learn from massive historical data, so they can learn, to learn the pattern from it. And our final goal is to predict the future events accurately. So that means we're going to train our model by using this input and to make our prediction as close as possible to the future events, and by essentially, by minimizing the error between them in the training data. Events is a special type of data because it is a heterogeneous structured, and it is also discrete type of data. So when we design the model typically should be complex because the pattern we want to describe is complex. And even so, it is still hard to comprehensively model because of the confoundings, because of other randomness factors, I will just try to detail a little bit about the related concepts and also the challenge, the more specific challenges. So the first related concept is called times, various type of times. which is very important when doing the event forecasting. So the first time is so-called the forecast time. That is the time that I restart my forecasting. And then the second type of time is the so-called event time. That is the true event time. Against that, I also have the predicted event time. And last one is the reported time. That's the time that the reporters or the first human being that observe that event. So what we want is that we want to maximize the so-called lead time, which is the first human being who eyeball this event occurrence. So so that means if we can forecast, if we can resolve the forecast as early as possible, that will be great. Of course, with high quality. Okay, so the other thing I want to dig a little bit into is the so-called social indicators. Traditionally, of course, we have the sensor network. We also have the traffic surveillance data, and now we have more and more social media data from different perspectives. So that is actually the focus, more kind of like a focus of today's tutorial, but typically it can be generalized to different type of data, not just social media data. So, but talking about social media data, I just highlight three aspects of its merits. One is the so-called adequateness. This is because we can get the data from very fine-grained spatial and temporal dimensions. This is Manhattan. Every single point is Twitter in each day. So you can see it covers every piece of corner in New York City. So whenever a small event happens, people will eyeball it and then post it onto Twitter. The other one is timeliness. Similar thing, right? So we can get the the event indicators in time. The last but not the least one is the so-called indicative or I would say informative kind of and also predictive signals. So for example, we can dig into some postings of people, and then we can see whether these people get a flu shot, or whether these people like some movie. So all of them are very meaningful for us to dig into, not just analyze the binary things like a sentiment, but also dig into the topics and what's gonna be lead by this topic. Although despite the merit, we also have challenges to handle the data just because we have those merit, right? Because the social media data covers every corner. It also contains a lot of sources. We have this more information also pose challenges to our traditional data to our traditional techniques. So the first one I will raise up is the dynamics. So traditionally, people would like to define some fixed feature for using machine learning model because we have fixed feature, right? But in social media space, we typically, for example, we can treat the hashtags as key feature, and actually they are indeed a key feature. Every time when we have a new event, then we will track the hashtag. But it is difficult, right? It is difficult to predict and to automatically track the hashtag, because hashtag is generated every day, every second, right? So that means we will need a dynamic model that can track the dynamic features. Next one is the multiple resolution of the social media data. So unlike traditional data, we have fixed resolution, spatial resolution, temporal resolution. In social media data, for example, some people may not disclose, they may not disclose their location at all. So we only know that he is on the planet. But some other people, they disclose their geotag, so then you can pinpoint these people. So how can we use mixture resolution data to do the prediction? The other one is the so-called data incompleteness. It is on the temporal dimension. For example, if we want to use multiple sources of the social media data, but actually their survival, their available time are different. So that will cause some problem, because if your model want to utilize all of the data jointly, then you can only enjoy the time that they both exist on the Earth, right? So then that means the more data sources you use, the narrower the time slot you're going to enjoy. The other one is the big data paradox. That means all the data in total is large, but individually it is small, and also noisy, as we can expect, because many people post very noisy postings like typos, etc. And of course, we also suffer from multilingual, multimodal. For example, in US, we have many languages speaking in tweets. Similarly, in Latin America, we have, for example, Brazil has over hundreds of languages they speaking in tweets. So if you do not cover any of them, then that means you give up that population of people. The other one is the heterogeneous network. That means we have actually the data is not just a plain data. They are connected with each other. For example, tweets connected to its users also connected to the locations. Tweets also connected to keywords. Keywords also have semantic meaning with other keywords. The user and the user also have friendship, etc., etc. So this compose some heterogeneous network that we need to consider because the information flow inside it. We also have some other challenges like dependencies among the events through the spatial and temporal and network dimension. We also have uncertainty, lack of label data, model interpretability, and lack of mechanism models. So I know it's kind of overwhelming a lot, but due to the time limit, due to time limitation, I cannot exhaustively introduce them, but I can introduce some survey paper that can look into them, help you on that. So considering time, I will just okay. So this is sort of a taxonomy of the major technologies in this domain on the spatial temporal event forecasting. So of course it can be split into three dimensions. One is the I call it actually is data-driven based. The other is generative and mechanistic based, and the third one is the mixture of them. So due to time limitation, I will not go into all of them, but I still want to give you some flavor on what how the machine learning can help to handle some challenges in the spatial data mining domain. So I just want to yeah, I may just want to kind of I'm sorry. Okay. Due to time limitation, I will just want to just. I think I don't pretty much have some time. I think so. Yeah. So I will just give you some more overview of the model. So this model is to use the famous machine learning framework on the so-called multitask learning for and use it to do the spatial event forecasting. So multitask learning is a framework such that we can treat different tasks and learn them jointly, and also preserve each task's unique characteristic, but also can share their common patterns, which is also concur the patterns mentioned by Ziheng previously. So this also aligns with the problem in spatial data mining. For example, one is the spatial heterogeneity, where different locations they have their characteristic. The other is the spatial dependency, where different locations they can also share some patterns. So multitask learning is a framework that we can just build a single model for each location's data. But over it, we can have some regularization, which is machine learning tricks on that. So as you can see in mathematics, it is just a designing of an optimization function. This is the loss. This is the regularization term. And of course, we can design the regularization term based on the spatial dependencies. So by designing different terms, we can handle different spatial dependency patterns, but also preserve the spatial heterogeneity. Okay, so I will skip the experimental results because it is much better than the one do not use it. So in the end, I will just read up several tutorials in the top conferences in data science and in big data, as well. I recently published a paper on the so-called event prediction in big data era, which is a very comprehensive paper that provide you the techniques and what the challenges it can handle. So that's all of it. Okay, thank you.
Andy?
Great. Yep, sorry. Finding all of my, there we go. Let's see, do we have great work? That was super interesting. I wonder, I wonder if, Ling, you could check out the chat because there are some questions that were coming in.
Sure,
while
yeah.
we have our next speaker. Do we have, is Nana next, Jensen?
Yes, it's me. I'm here.
Hi, Nana. Great.
Can I share?
Yes, you can share your screen.
Awesome. I'll do so now.
Okay.
Can you all see my screen?
I can see myself on the live stream. There we go. Okay, now we can see your Google Slides and
okay,
looks
cool.
good. Okay.
Let's dive into it. Hi, everyone. This is Nana E. I am currently a machine learning engineer at Development Seeds, and I also lead Earth data analysis. Development Seed is a small for-profit company. We always taking on projects related to Earth science. For example, we're building data archive for NASA, building Earth infrastructure, Earth data analysis. We work a lot with OpenStreetMaps and trying to build a impactful products or data visualization for our clients by specific problem we're solving. When it's come to machine learning engineer approach, there's three things we really care about. First one is innovative problem solving, domain experts, increasing our domain expertise by partner with organizations like World Bank, UNICEF, NASA, and ESA. We're trying to help people to solve the world's hardest problem. That's always the statement. And by partner with people like a big organization and who care about the social goods, right? That we're increasing the domain expertise and also understand the science question behind the problems. And come to algorithm development and engineering, we always have trying to solve as large a scale as we can. For example, country, continent, or global level. And we trying to open source everything we create, from training data sets to model training pipelines. And open source is a core value of Development Seed. We just build things, we open source it, we want to benefit the wider community. And we also want to collect the feedback from people. And that's something love engaging with the community. That's by open source tools. And when we trying to solve a problem, we always have ethical impacts in mind. We're trying to make the data or data layer more actionable to decision making that will foster more responsible or sustainable policy making that will benefit many generations to come. So let me jump into the detail. And this is not one of the problems we're solving, by the way. So come to the real world ML applications. I would say we can divide it into three direction or category. First one is we're trying to help people to develop machine learning application that is going to be help them do smart investment for international developments. For those projects, for example, we're working with World Bank. We worked with World Bank. This project is already done, mapping high voltage grids. And we're working with Chinese Ministry of Commerce, working on mapping rubber plantation and rubber cultivation risk, and working to promote equity, working with UNICEF to map every school on the map with machine learning. And we also sponsor or funded by Microsoft AI for Earth and Global Wildlife Conservation to working on a workflow that to mitigate human and wildlife conflicts with computer vision and deep learning. Nature disaster mitigating, we're working with World Bank now to searching for vulnerable housing at the street level from Street View. and working with NASA using satellite machine learning for COVID-19 impacts and responses, right? And also like working with NASA for hurricane intensity mapping. So I cats and dogs are cute. So I love to use these slides to just like help bring the audience to understand like what is the deep learning or computer vision algorithm we're looking at. When it's come to supervised machine learning, there's a few categories we're looking at, right? For example, image classification, you make a judgment if that objects appear on your image or not. And object detection is you draw a bounding box and to tell the approximate location of your objects. Instant segmentation is you draw a boundary around the pixel like belong to your objects, right? So that's being used by earth science cases like land use and land cover mapping. It's semantic segmentation. So how can we jump from cat and dog image or model to mapping road network from satellite imagery? So this is the machine learning workflow already exists before I joined the DevC. Basically, it's mind-blowing to me because I come from that traditional earth science machine learning background, which is you download scene by scene of satellite imagery and you work scene-based, like write a random forest to classify, for example, right? And how can you make the model predict road network at the real time? And so it's mind-blowing, and I want to learn about it. I want to use it. I want to develop a workflow that it is going to be fast as this one is real-time road network mapping. So it's come down to a tile-based satellite imagery, right? Just think about like when you zoom in and out from Google Map, it's really fast because it's tile-based. When you keep zoom in, it's to zoom 18 or 19 is basically like 50 centimeter of satellite imagery, spatial resolution of satellite imagery, right? So the idea of tile-based tile satellite imagery is you can read in your satellite imagery chunk by chunk. And by reading this chunk by chunk, you can parallel them to a multiple machine. And then you can build a deep learning or machine learning algorithm on top of it. And you can train it very faster because the data is chunked and you can parallel them. And when you have a well-performing machine learning model, you can also predict it very fast because the data is being chunked. And that's how we're searching for the tiles from higher level, zoom level 0 as a global level, and to like as low as zoom 21, right? Like by just few centimeter. And come to the real machine learning use case, right? Like for example, smart investment for international development, which is mapping high voltage grids. Why we need to map that? The science question or problem behind it is, you know, like those high voltage grid is very expensive. You don't want to spend like $1 million US to build 1 kilometer. And when you go to the field, you find out these high voltage grids already exist, right? So we want to have all these high voltage grids on the map. And the second problem is mapping every school in the world from high resolution satellite imagery, right? The science question to define is what is make school a school? How is different from regular residential buildings? And how can we narrow down the feature that define the school? So that is the science question. And how can we develop a deep learning to utilize this the school feature and also like high resolution satellite imagery, and searching at the national level or continental level of schools and put them on the map. Another one is searching for vulnerable housing at the street level, which is not satellite imagery basis, it's street view imagery basis, right? People living in the neighborhood with poor building standard are likely to be killed by a disaster. So government and local community want to help those people to retrofit the structure, but fixing the building isn't the issue, but funding them is very hard. So how can we use computer vision and machine learning to search for this vulnerable house in a faster manner before the nature disaster hit, right? Every machine learning model come down to whether you have high quality training data sets. We are very lucky. We have a 5-6 professional mapper in-house. They are based in Peru, and they basically create every machine learning training data set for our pipeline. And they are professional mapper. They map super fast. And we turn to just sit down with our client and partner to understand the science question and what machine learning to build. And on the other hand, right, like it's end-to-end machine learning. Like we create a training data set until we produce the national or continental level of the map for our client. So data team is not only like create a training data set, they create tools, and which is the feedback to the OpenStreetMaps. They map millions of map objects every year to the OpenStreetMaps, and they also create a tool called OSM Seeds, and which is the mirror of OpenStreetMap, that we can utilize the millions or billions of map objects exist in OpenStreetMaps. But like not every client or partner we work with wanna push the data to the OpenStreetMap directly, or OpenStreetMap sometimes not interested in the data that our clients interested, right? So OSM Seed is the perfect infrastructure that we can mirror the OpenStreetMap, and on top of that, we can use all the ecosystem tool editor from OpenStreetMap. We can refine it and push back to as the open source to the community to use. Another tool is called Label Maker. Basically, it's pair satellite imagery with OpenStreetMap, originally with OpenStreetMap, and later, right, like label data created from OSM Seeds. And sometimes, as long as you create your own label data and you have your satellite imagery, Label Maker can help you to pair those satellite imagery and label data for image classification, object detection, and semantic segmentation training data sets. And then come to training the model on the clouds, right? We working with very diverse client that they have a habit to hook to particular cloud provider. A lot of time we use AWS, but sometimes like we need to use Microsoft Azure and Google Cloud platform, right? Like how can we containerize or standardize our machine learning pipeline that we can basically package it and push it to the cloud and training. We get into a open source tool called Kubeflow. It's originally developed by Google team working on the internal machine learning workflow built on top of Kubernetes. And Kubeflow, the amazing part of it is like you can build component or you can build a chunk attached to, for example, like model training component, you have a model evaluation component. So your model will just like train on multiple GPU machine, like spin off, like you can spin off like hundreds and thousands of machine, right? Like one machine got terminated by any accident, or, like, for example, you were just using AWS Spot instance that you're not bidding the highest price, so your machine got terminate in certain region. But Kubeflow will keep your workflow and just like send basically the worker to work to another worker that is available in the region, for example. So your work is not going to be terminized by any accidents, and keep training until you find a best training model. And this best training model, again, right, we will containerize train the model. And such a train model can turn into we call TensorFlow serving image. Is going to push into Docker Hub, and we can pull the model whenever it's ready. We're ready to run a larger scale model inference. So what is the larger scale model inference looks like? We also have, we built 2 different tools. One is called Chip and Scale. This one is particularly working with AWS cloud resources. We will have all this tiled image. Basically, each tile is 256 by 256 pixels. And, you know, we will have millions of them queued it up to the AWS, hit the AWS Lambda, and spin up the containerized model. And when the tile hit the containerized model, it will make a prediction based on the trained model, and such a output will push to the database. And building an ML enabler is going to be our kind of like machine learning hub that is not only going to help us visualize how our machine learning model perform at the real time. Basically, you just need to drop in machine learning model that already containerized, and drop arbitrary AOI. So the AOI is going to pull the tile where you pointed to, right? Like a tile endpoint from Planet Lab, or tile endpoint from Maxstar, or, you know, like you can create your own tile survey from Sentinel-2 or any star imagery, for example. You can serve them as a tile endpoint. So this AOI is going to fetch the tile. You know, you can do as many as you can, and an ML enabler gonna visualize the machine learning outputs, and you can adjust the confidence scores ratio. So when what mapper see or map validator see is the tile like color by red color. For example, red color is predicted as school. So mapper will go in and validate and make it green. For example, that's correct. Tile is school. So such validated tile can then export it and again, package it up and as a training data set, or, you know, package it up, pass to our client. So here is we're trying to integrate human with machine. Again, our mapper work a lot with OSM, and by like speeding up the workflow, which means like we can speed up human to create a map objects to OpenStreetMaps, right? And also like machine is doing more kind of like repetitive, tedious, like larger scale prediction, but human is more doing like a creative and is validating and creating a more precise map. So we want to make those human and machine integration much faster way, right? And when it's come to mapping the high voltage grids with WordBank, our machine learning and annotation pipeline map the whole entire high voltage grids of Pakistan, Nigeria, and Zambia in 18 days, which is machine learning model help human to map this faster. Another one is working with UNICEF to map every school on the map, right? So the latest effort is adding 7,000 previous unmapped schools across Colombia and 11 Eastern Caribbean nations, and like looking at Zoom 17, which is 1 meter resolution satellite imagery. We are looking at about 52 million tiles, and by using the machine learning, helping human to map or searching for school, which is like speeding up a lot. And now we are looking at mapping schools in West Africa, East Asia, and South America. And when come to nature disaster mitigation, like we develop this machine learning pipeline that like looking at the street view imagery and make a prediction. On the left, you are looking at the algorithm, particularly searching for garage door and windows. Like we can predict the approximate size of this window, door, and garage. And this, the left figure is looking at all these attributes come with a houses. For example, house type, if this is residential, critical infrastructure, or commercial, or mix, or like looking at materials, what material when to build the houses, and how this material is going to make the house vulnerable to certain nature disaster. And also we're looking at the house condition, good, bad, poor, right? And we're also looking at the house vintage, and also like construction type. All these things like once make a prediction by the machine learning, and it's pushed to the database. So local official can go to the database and quickly search by filter the certain prediction saved in the database, so they can target the houses or people or neighborhoods that is going to be vulnerable to certain nature disaster. So they either can help them building a better house with better material, retrofit it, or they can evacuate those people to a safer place when the nature disaster comes, right? Such a workflow already implemented in multiple South America and Southeast Asian countries. So conclusion is the approach we normally take is understand specific science question behind the social good problem through collaborating with our partner and domain experts, and applying existing deep learning best practice proven methods in a novel way. And when it's come to the tool, we're trying to standardize our machine learning tool pipeline. We open source them, and again, like by open source them and have a wider contribution back to the tool itself, is going to keep them like more reliable, reusable, and efficient and scalable. And all the tool we built and I mentioned today are open source, and you can take a look. And you also can find me on GitHub. You will find a lot of tool I'm writing, and also like tool and I am contributing to earth science in general. And now we're working with a lot of group like NASA Severe, like looking at crop type, and also building some earth science particular related machine learning training material, I would say. So get people's hand dirty, and how to utilize all these open source tools, and to do earth science more faster and more efficient. That's it.
Great. Thank you, Nana. That was a great talk. I think I've seen parts of that before, but it's great to see how you guys have expanded those projects. So we've got 15 minutes 15 minutes left. Jensen, do you want to take back over?
Oh, I think we have another speaker.
Oh, yeah. Oh, we have 4. That's right. Okay. Sorry, for some reason I'm thinking 3. All right. Who do we have up next? I'm looking at our list here. Is our next speaker on, Jensen?
Diego, right?
Hi, yeah, it's Diego.
Oh, you are Diego. Sorry, I didn't see your name listed. Oh, there you are. Okay. Are you able to share your screen, Diego?
I'm trying to share it right now. Let me know if you see it. Do you see it there?
Yes, we see it. Looks great.
Perfect. So I only have 15 minutes, and I think we're going to start posting the questions on the chat. And so I'm going to start real quick and go ahead. So thank you for having me here. Every time I come to these sessions on machine learning, I'm always wondering what's my job here. And I think, this public-private partnership to increasing resilience and hence socioeconomic value of data kind of fits the topic. And then when it comes to our own session, I think I bring a bit of dealing with the assumptions and complexities, or both, that include the human and machines that were mentioned in the last slide from our previous presenter. And so anyways, I'm gonna discuss a little bit of this project in which we're trying to connect agricultural stress indices to seasonal forecast systems. And so let me see if I can switch here. As you know, many of the countries and developing countries worldwide are based in their agricultural, their economies on agricultural endeavors, and usually the systems are rain-fed, especially for smallholder agriculturalists. And although there are several systems currently working on monitoring agricultural drought and agricultural stress, or vegetation stress overall, they're not necessarily connected yet to the next generation of seasonal climate forecasts. And therefore, we've been trying to develop a general approach to do this. And we call, and you're going to hear me saying this a lot, the next gen. Next gen is the next generation of seasonal climate forecasts based on the multimodal ensemble from the North American ensemble, validated at country level, cross-validated and verified at country level for each of the countries we've been working on this project. And what I'm trying to do here is showcase how we can not only forecast precipitation and temperature, which are obviously important, but also the question and answer here is, can we start to forecast agricultural drought? Vegetation stress that is to a point where it becomes bad for plants and for crops and for yields. So to do so, we're going from big data actually to the source, because this current project is on available for monitoring agricultural stress, deal with a lot of data, work at a global scale, sometimes at a regional scale with big data, but they haven't been able to reach the smallholder users, right? Those little farmers with 0.5 hectares in Guatemala that don't have first access to these systems, obviously, but then the system doesn't have the answers for this type of users. So we consider them in the development of this general approach, and that's going to be my talk, how we went from the seasonal forecast systems to being able to forecast agricultural stress or agricultural drought. So for those who don't have much time, we were able to develop a model that can forecast NDVI, the smooth version of it, which is available on NOAA's STAR webpage. In addition to precipitation, we use temperature, mean temperature, as well as a predictor for the predictant. And aside from the traditional below normal and above normal categorical values, we also presented the information on what we've been calling at the RI the flexible forecast system, which I'll get in a second. The overall goal is to determine that if we've developed a general approach. Can it be applied to most of those agricultural monitoring systems worldwide that are based on NDVI? So that's our premise. And so these systems are climate information systems, but they are being examined more and more by the users because they want to be part of the development of the systems so that their demands are satisfied. I'm going to use, again, as I was saying, the example from Guatemala, from Guatemala's dry corridor, an area known for obviously droughts, but also famine, food insecurity, and poverty. And so World Food Program, FAO are currently working in the region, and it would be very relevant to develop a system that can assist in seasonal forecasting of these indices. The premise is that we will be able to anticipate agricultural drought month in advance, and not only monitoring it in near real time as it is done currently. So users in Guatemala, this is a recent evaluation of what the users in that region are demanding in terms of a climate system. And this is where it connects to vegetation health systems, to NDVI systems. They lack the spatial and temporal detail required by the users. They want to be involved. They want to co-produce the systems. They want it to be a two-way user-provided communication, not only top-bottom, but very inclusive system that they can download information, plain language, logical structure, visual aid, which is very important for this particular group of people or users in Guatemala. And they want the recommendations to be linked explicitly to the timeframes of decision-making processes. So I guess relevant to our session, the question is, well, can we satisfy all these different demands using big data, machine learning? And how can we incorporate those decision-making processes to inform the systems that we're building? Users don't want the loading dock model, whereas you park there, you put the information in the dock, and then you say goodbye. They want to be involved, especially in this dynamic world where sowing and harvesting dates are changing, where precipitation and temperature regimes are changing. So they need to be part of it naturally because the dynamics of the system call for it. Now, that was on the user side. What are the gaps on the monitoring systems? Same for the same region. There's a gap, or there's several gaps when it comes to identifying croplands. When it comes to identifying calendars for these crops, where are these crops located, and what is the intensity that we are, the soil intensity? What are the crop types? What are the crop management data? There's a lot of gaps when it comes to data. What is the yield, etc. And there are gaps associated also to the methods. So we need better predictions for yield and crop production, and understanding between discrepancies that are usual in the remote sensing world versus the real world, and tools or methods to synthesize the information for decision makers. So at the end, what we're proposing here is to start to bridge this gap, obviously, and considering the users when doing so. And so I'm gonna start talking a little bit first on how we have been developing the next generation of seasonal forecast. We basically, I don't know if you can see my cursor, but we have this outputs of the North American multimodal and sample models, let's say for precipitation in a gridded format. We assess the raw predictive scale against gridded observations, which can be, I don't know, chirps, it can be CPC, it can be weather stations themselves, and then we correct for bias in the mean, bias in the variance, and as you know, you have to correct for these bias when you deal with the model outputs. And then usually we stand here where we generate forecasts on below, normal, and above, so only 3 categories, and assign a probability of occurrence. However, this next generation of seasonal and sub-seasonal climate forecast now incorporates the probabilistic space of all those models, ones that are sample created for that particular country, which allows us to create what we call the flexible format system here. And I'm going to zoom in. This is obviously Guatemala with a forecast, but I want to zoom into this chart. And you can see the climatology in blue that has been smoothed out versus the observed, which is in black. And then you have the forecast, which is the red line that you can see there. This is a seasonal forecast for April, May, June that was initialized in March the 1st. So you have a lot of information here, including, let's say you're planting beans in that region of Guatemala, and you need at least 100 millimeters of precipitation for April, May, June. You will read this going up and tracing the probabilities here of occurrence, which are basically the same as the historical, as the climatology. But if you are a coffee farmer in that same region, and you need at least 200 millimeters of precipitation for that same period, probabilities of getting that are close to 0 versus 30% of the times in the climatological world. So this is pretty much how you interpret this. We call this the demand axis and the supply axis when it comes to precipitation. You can imagine any other variable in this x-axis and the associated probability on the left. How good are we, and how many months in advance we can start to feed forecasts? For Guatemala and for the region of interest, which is in this square, we're pretty good. This is a forecast initialized in February for March, April, May, April, May, June, July, and June, July, August. The reason why you're looking at this inverse diagonal here is because it is the period of critical phenological stages for corn in that particular region, and hence it is our critical time for this particular study. This is what you're looking at is the 2AFC category, basically a score that measures how often the forecasts are correct. The closer to the red or 100 here, the better. And so you can see the blue is pretty bad if you consider 50 equals to the climatological record. So on top of 50, you have more information in the system in the model than you would if you only consider the climatological historical records for that. In this case, precipitation. I have many other scores that I could show you, including the rock curves, ignorance, and grok. But for the sake of time, we're gonna just focus on this region. We did remove the forest cover, and we did some other treatment to the regions that we're gonna work at, because we know NDVI saturates at tropical regions with forests, specifically conifers. So we collected the information on annual agriculture for Guatemala and focus on, this is the whole dry corridor in Guatemala. We focus on a sub-region of the dry corridor towards the eastern part of the country. And then we created a calculation on the water demand for corn and beans for this region. And the way we got to adapt this to this region was basically through a crowdsourcing, and I'm gonna get there in a second. So there's a lot of assumptions when we're doing this. No irrigation systems in place, water demand on the equal evapotranspiration regimes, which we know is not necessarily the case, equal soil characteristics, same genetic material. There are a lot of assumptions when we are working with remote sensing data, independently from checking it on the ground. And just so you have an idea, this is how it looks. This is corn being planted in the region successfully and healthy, who had enough water at that point. And this is another village in the dry corridor where the starting of the reproductive corn stages didn't go well due to lack of precipitation. So that's what you would perceive also in the satellite, in the NDVI in this index. And so you have these calendars that you work with, right? We divided the country in several regions, usually climatological regions with its own sowing and harvesting dates, et cetera, et cetera. And this is the type of calendar that those big systems are currently using. There's another set of assumptions associated to that. The most important here is that the harvest for the dry corridor here, called Región Valles de Oriente, is highlighted here in orange, and it says October, November. So that's an assumption here if we only consider those data sets. The truth is, once we had the opportunity to work with farmers on the ground and with extension service agents, we interviewed 90 of them, 30 for each of the departments, to figure out that, yeah, they harvest October, November, but that corn has been standing there for a couple months because it is used as a base for the beans, which will naturally mess your signature on the NDVI signal. but the actual fruit is ready to harvest in August. It's ready to be collected on August. So that is invisible to someone working at different scales and who has not approached the farmers on the ground to establish that. And so we start to match this demands by the users with the providers and understand how we can start to, once we have such a system like NextGen with the capabilities of forecasting precipitation and temperature, well, how do we make that information adapt to these demands on the ground? And there are some that are naturally responding to each other. Well, the co-production will help us map crop types, will help us map crop calendars, understand cropland themselves. Two-way user-provider communication will allow agricultural production area and yield data to be collected. And so there are natural connections between the gaps and the demands. And we believe we can start doing that. So participatory process at the center of this validation of the croplands and maplands. This is how it actually looks after they validated. Each group had 3 different groups that validate this. And they started to give us this information back so we can also incorporate it into the models. For instance, this is a agricultural calendar for each municipality within the department. The department is the black bold line. So we got to the sub-municipal level information on the sowing and harvesting, as you can see here. Same municipality was Tatoya, the lower part and the highest part of the mountain. Validated among them all, and so we established that the demand for water, the water demand for crops in this region was up to 90% on June, July, August. And we know the harvest actually occurs in August when the produce is ready. So we confirmed this, and then we move forward to understanding our correlations on the satellite world and the big data world. And so we use precipitation as a moisture supply proxy for soil and temperature as a proxy for atmospheric moisture demand. Overall, together, what we are trying to get here is an approximation to soil moisture, which is where plants get their humidity from. We use the model output statistics to correct for bias, and as I was saying, using canonical correlation analysis. These are details on the development of the forecast itself, but we applied that to the Primera corn season in the region, May season, for June, July, August. And obviously we based this on an agricultural calendar that has been now verified on the ground. And we run several experiments. We use precipitation anomalies from the forecast system against NDVI, against the smooth NDVI, against the vegetation condition index. And we also did experiments with precipitation plus temperature anomalies from the model itself against the same predictant. And you can see the goodness index there as a Kendall-Stahl correlation, having next-gen precipitation anomalies and temperature anomalies against smooth NDVI, the best model possible. And so, for instance, what it says is that if we have a precipitation system, a forecast system that can inform users beginning in February, as you can see here on the far left, initialized in February for all this month, you have the highest predictive skill actually initialized in February for June, July, and August for that region. We have it obviously for March and for April too, a little bit for May, June, July, initialized in February. And obviously the closer the month gets, for instance, initialized in March or April, closer to June, July, August, the best information and the predictive skill that we get. It is obviously not only necessary to assess how often it's good or bad, but how good the discrimination skill is for each of the categories and how reliable that model is. Basically comparing the observed frequencies versus the forecast frequency probabilities and trying to establish how often and how good that model is. So we have a good model built here based on that.
Now, Diego,
yes.
Hey, sorry, this is Annie. I just wanted to give a quick time check. It's about five after the end of the session. Yep. I know you didn't have quite enough time. So I was just going to ask if you could wrap your session up in the next 5 minutes, but then we can allow anyone that wants to stay on to ask questions could do that.
Thank you. This is actually the second to last PowerPoint. So basically after creating understanding all those systems, we can, with this map room, we can see what was reported on this last column. In this case, we use Vegetation Health Index because it's of use for one of our partners, the FAO. Precipitation is measured by chirps, ranked precipitation there and the forecast from our system. And in this case, you can see June, July, August for as back as 1996. And it helps triangulate information on what farmers reported on the ground, what the vegetation index is saying, and I'm going to zoom in here, and how good or bad our forecast would have been for decision making in anticipation of that drought. So it also showcases that sometimes we have El Nino at a bad year, but sometimes we have El Nino with not a reported impact on the ground as we would have expected. And so this information can also be translated into quantitative information by having the farmers report what a good year meant on average, typical year and bad year. And this is how we're trying to translate a forecast into measures that can be then considered adaptation strategies for that particular region. The next step for our program is to move forward to our, helping other platforms integrate this sub-country level crop forecasting service to anticipate droughts month in advance and therefore allocate resources, both financial, people, and so forth. So I think that was it on my side. Thank you.
Great. Thanks, Diego. That was a really great talk. It is 3:36, and I want to be respectful of everyone's time. So if you have to take off, we understand, and I'll thank all of our session presenters. This was a good series of talks, and if anyone, oops, I think that's probably a Kiko chat note. If anyone would like to stay around and ask questions of our presenters, I will not close the Zoom. I'll leave it open. I would encourage you to do so. So thanks, everyone.
Thank you, Annie.